Well, welcome back, folks, so far. We'll get started in less than a minute. Well, it's official. Looks like class has started. Hopefully, we get more people that come in a bit later. I'll just assume that they're tired after getting through our first exam. Well, after getting through our first exam, I'm going to start receiving emails from the various testing center that contains your scanned copy of your exam. I'll be doing the grading of your exam over the weekend. Once I have it graded, the full set for the class, I'll start emailing back the exams to you one by one. So watch for your ISU email. Once the exams are completed, I'll have grades posted here, and your completed and graded exam is going to be emailed right back to you. Well, I don't have too many announcements to start us out today, but any questions or comments at the moment? Okay. Well, so far we have quiz 3 that's due today, and the new quiz 4 has been posted. I forgot what this was even over. I wrote this a little bit earlier, I think on Monday. Quiz 4 is almost there. Forget this takes a bit to load. Looks like an application problem. We're doing one that's pretty similar to this one, it turns out. We're on the very last problem of section 4.2. So we're going to do a problem similar to the quiz 4 problem. You can use work here as kind of a guide to get through the quiz problem as well to refer back to. After we finish section 4.2, we'll move into 4.3. And this will be the last section we're covering in our chapter 4 on systems of equations. After that, we'll be turning over to more interesting things in algebra. Chapter 5 will be dealing with polynomial functions. First, starting off with properties of exponents. We'll be getting into factoring equations, solving equations involving degrees 2 or higher. But for the moment, before we get into all that fun stuff, we have just a couple more application sections to finish off. So here's where we left off. It was last Thursday, last week, going into a weekend right before the exam. We solved several problems like these on example 5, and this is kind of our third run. I copied down the formula down below just for a quick reference. The idea is we need to use this formula here for uniform motion to track the distance, which is equal to the rate times the time, to solve these kinds of problems. And there's two unknown quantities that we're trying to find on these. So we need a system of equations. We expect to build two equations. Here's how that all comes together on this one. We're told a jet travels 3,520 miles against a jet stream in 5 hours. So jet stream, just think of as like a river of air pushing the plane along or fighting against the plane since it was going against it. But when it was going with the jet stream, the air was pushing the plane. And we're told it went further, 4,020 miles in the same amount of time. So still 5 hours. So that's not a lot of information. It's all contained in one sentence. But when we go to break it down, it really does kind of expand out into a really impressive set of information. What we're going to solve is what is the rate of the jet in still air? How fast is this jet going? And what is the rate of the jet stream, the air that was sometimes pushing it, sometimes fighting against it? So this really boils down to just breaking down the information very slowly and methodically. Let's start right here. The jet was either going with the jet stream or against it. Before we go to that, kind of jumping the gun, probably the number one best thing we should do as a first step is really just define the variables. So before considering that first sentence, we're asked what is the rate of the jet in still air. So let's just write down x equals the rate of speed of the jet. I'll just leave it like that. I'll leave it implied that we're talking if there was no air whatsoever. We also want to know what is the rate of the jet stream, how fast is that going? We can label that as y. Y equals the rate of speed of the jet stream. Okay, so now we've got variables to work with. Here's how we can start putting the information together. It might be a good idea to color code these as we go. Why not? So X in blue, Y in green. So first situation is the jet was going against the jet stream. So let's write against the jet stream. And when we're going against the jet stream, we need to tie in all the information that we can discover in this sentence here. Essentially, we're just writing out what was the distance, what was the rate, what was the time. We're told the distance was 3,520 miles. So let's begin there. So D is 3,520 miles. The time was 5 hours. So they just straight out told us. That's nice. And finally, the tough thing about this problem is getting R down, the actual rate of speed. Well, it's kind of confusing in the way because the rate of speed is in components, X and Y. Here, we would start with the speed of the jet itself, X. But we're told we're going against the jet stream. And because we're going against, we're going to subtract off the speed of the air that's pushing against the jet. So X minus Y. So that word against is what's leading to the minus right there. Let me try a different arrow. But with all that together, we can use the formula distance equals rate times time. Put this all together using the information we have, and the equation becomes, for distance d, 3,520 equals, for the rate of speed r, that's our x minus y that we plugged in right here. We need to put parentheses around it because the time t has to be allowed to multiply. So x minus y here. Then for the t part of the equation, we just take the 5 hours and multiply by 5. So all of that stuff from here to here, just one fragment of the sentence, gave us this information. The ultimate thing we wanted is this equation, right where the red dot is. If we can get a second equation just like that, we'll be able to solve them both quickly. Really, most of the work here is just transferring the ordinary English into the algebraic stuff we have down here. But hey, it's halfway done. Any questions getting to this point? Okay, well, let's turn over to this part. So this time we're going with the jet stream. So let's label that with the jet stream. The jet stream is pushing against the plane, and that's why it went a greater distance in the same amount of time. So distance is 4,020 miles. It said the same amount of time, so we interpret that. T for time is back to 5 hours. Then finally, we need to write down the rate. This is the tricky part of the equation, even still at this stage. Like before on the left, we start with x, the rate of speed of the jet itself. But if we're going with the jet stream, that would mean we're adding the speed of the air to the overall speed that the jet is going, the overall rate of speed r. So we'll go x plus y on this equation. So this conveys all the information highlighted in gray. We go back up here to the uniform motion formula. Like we mentioned before, we often use this twice in these problems. So distance is rate times time. And back to the same comment we've mentioned a lot in algebra. Quite a lot of the algebra we do is just making the right substitution. In place of distance, see the information above. It was 4,020. In terms of the rate r, highlighted in yellow, we have the x plus y. So throw that in there. And the amount of time t was the same, so it's just going to be times 5 once again. So now we've got it, folks. Two algebraic equations in variables x and y. Once we solve for these, our work is totally over. A good strategy on this one, just like on the others, should be the addition method. If we divide out 5 on both of these equations, and don't divide evenly, which is nice, the minus y here and the plus y here is just going to cancel off. So let's just start by dividing both sides of both equations all at once by 5. We'll need a calculator, so let's get this thing going here. On the left, it's 3520 fifths, so 704. I'll change the order of the equation as well, just so it's a little bit nicer to work with. So 704 is on the right-hand side. We divide out 5, so x minus y is on the left. Then just do it all over again, 4,020 now divided by 5. That comes out to 804. So 804, changing the order so it's on the right-hand side, is equal to x plus y. So now these are not the worst equations. These would be some of the easier equations from section 4.1 to solve. If we stack them on top of each other, go x minus y equals 704. That was the first equation. Right directly under it, x plus y equals 804, the second equation. Then we can total them together. For x, we have two x's. Variable y cancels out, and it's going to be equal to, let's see, this should be doable, 8. 0, 7 plus 8 gives us to 15. So twice x is 1508. Let's divide that by, oh, wrong thing. Divide that by 2. We get 754, but that's our solution x at that point. X is now 700, and I already forgot the number, 754. Let's write it this way, miles per hour, because x is a rate of speed in that particular unit. Halfway done with the problem, all we now have to do is solve for the y variable. Here's where we make a substitution in for x into that position. That x becomes 754 plus y is equal to 804. So if we subtract 754 from both sides, we get just that y equals 50 miles per hour. And that's the solution for y, the speed of the jet stream. So we got it, folks. If the plane did 754 miles per hour and the air was 50 miles per hour, going against, the plane would have done 3,520 miles, and going with, the plane would have done 4,020 miles. Well, that's the conclusion on this problem here. Any last questions or comments getting through this one? Kind of impressive amount of writing from, I have to say, a word problem that was just 2 sentences. I think section 4.2 has some of the trickier applications when it comes to the uniform motion type of problems. And we're going into another set of applications in 4.3 called the mixture applications. But I also think that once you get the hang of how mixture applications go, really it's not too bad. These are probably going to be the tougher problems in chapter 4. So I think I've saved it twice now, but let's make sure it saves. And we'll take a look at those new problems in section 4.3. So notes are pretty similar looking. There's not a whole lot of information here. Occasionally we might need formulas, and those formulas are going to be put right in context. But first, examples 1 and 2 are just really quick scenarios of mixture problems. When we get into the next examples, we'll be using the formula for simple interest. So the interest equals principal times rate. But in all the problems that we do in this section, we're going to take time to be 1 year. So it's just going to be interest equals principal times rate, not the times time. So we'll simplify that formula a bit as we use it. Well, all these things are mixtures of some kind. This one is mixing raisins and nuts, so kind of riveting information there. This one seems to be something in chemistry, mixing chemical equations, some with one with or chemical solutions, one solution with 20% acid, one with 30% acid. And the other one is just mixing accounts at different rates of interest being invested for some total amount. So some way, somehow, all of these are the so-called mixture problems. They're sometimes really confusing to start, but again, once you get the hang of it, these really are not too bad. I think they're actually even slightly faster as well. So first thing we need to do is read through the context. No matter how brief, there could be a lot of information there. And this one is just one sentence. It says, how many pounds of nuts, which sell for $6 per pound, and raisins selling for $3 per pound, should Kurt combine to obtain 120 pounds, so Kurt's buying a lot of stuff, of trail mix that costs him $5 per pound. So maybe Kurt has some other side hustle. He has a business that he's working. He needs 120 pounds of a trail mix that he's working on. Needs to come out to $5 per pound. And he's just using these two ingredients, the nuts and the raisins. So those are two unknown quantities. Let's highlight these and give them variable names. We have nuts selling for $6 per pound, raisins selling for $3 per pound. So we could go X and Y before, but let's try N and R. N is going to be number of pounds of nuts, which sell for $6 per pound. R is going to be the number of pounds of raisins. So this would be our pretty much step one of really all the problems we've been solving in chapter 4. Step 1 is just to write down what the variables are, give them some kind of description, and even if we lost our way on this, say this is a problem that's really on exam 2, just by doing step 1, you would get some partial credit on this problem already. So the more you do this part right here, it's just going to help you put all the information together, as well as rack up partial credit if you lose your way at any point. Well, next thing we have here is that there's going to be 120 pounds of trail mix. So that's a total in a certain sense. The total pounds is going to be this equation. It has to come out as 120 pounds, so equals 120. And the way we get there is, well, N is the number of pounds for the nuts, R is the number of pounds for the raisins. So we're literally just going to add those two variables together. It'll be N plus R. So we could consider this step 2. If this was a 5-point problem on the second exam, this would be 1 point, this would be the second point. The third point would be to write down the other equation, and that's going to come from this part. There's a cost per pound that Kurt, interesting fellow, is going for exactly $5 per pound. So using that information, we recall he's buying 120 pounds of this mix at the rate of $5 per pound. So the natural question we want to ask is, how much money is Kurt putting on his Visa card, or maybe he's shelling out cash for this? So this is going to be the total cost equation. Total cost is going to involve this information, $5 per pound. And let me put in the unit on that one, LBS for pounds. But he's also going to multiply by 120 pounds. And you know, if I go that route, put in units, I have to put in the units accurately. Give me one moment. $5 per pound as an accurate unit would be $5 divided by LBS, the pounds. That's the tricky thing about units. It starts to become a lot of writing when you put them in accurately. This is a total cost equation because the division here by the unit pounds coming from per pound, and the pounds right here are just going to cancel out. So we would have a cash amount right here on the right-hand side. And now we wonder, how do we get to that amount? This is where these two parts finally come into play. We still haven't used the fact that the nuts cost $6 per pound, nor the fact that the raisins cost $3 per pound. But now we can say N is going to be the number of pounds of nuts. So in the total cost, it's going to be 6 times N. Thinking about that, it's $6 per pound. N is the number of pounds. So that's the contribution to the total cost coming from the nuts. Do it again for the raisins. We have $3 per pound for raisins. So we would take 3.00, just to remind us that that's the dollars per pound, times the variable R for the raisins. So that's our total cost equation. This is the step 3 in the process. Kind of at an angle just to mention this whole equation is that step 3. Maybe it's better to write it this way. Let's use the arrow system on this one. And on partial credit, this would be 3 points out of 5. The remaining 2 points is just to solve whatever we have. Even if you made a mistake on the equations, if you solve your equations correctly, you would get all of that partial credit on that side. And pretty much that's how all the equations are going to be graded on partial credit, whether they come from section 4.2 or 4.3. Well, any questions at all, folks, on the hard part, doing the setup? Okay, well, let's multiply this through here. 5 times 120 is going to give us 600 to work with. Then we can now simplify this down to 6n plus 3r is equal to 600. I think the substitution method probably works just fine on this one. And it's good to practice just for the sake of variety as well. You can solve for either variable here on the easier equation. Let's solve for maybe r. Subtract n from both sides. R is equal to 120 minus n. So this is going to go in the position for r on the right-hand side equation. So that copies in. Now we have 6n plus 3 times. I got the parenthesis, but forgot the 3. 3 times 120 minus n. Equals 600. Now, not too bad algebra. We'll distribute that 3 in. 6n plus 3 times 120 is 360 minus 3n equals 600. We can combine our like terms and have 3n plus 360 is 600. And now we're just about on our way. Take 600 minus 360 will give us a 240. So 3n is 240. And 3 happens to divide in that evenly. 3 goes into 24 8 times, so n is now equal to 80. And this was in pounds, so this would be 80 pounds altogether. So this is what Hertz trail mix is going to look like. It's going to be, oh, my color coding is a little off here. Sorry about that distraction. So I had R. Then we're solving for n. I see where I lost my way on that color coding. N is in blue. N is the number of pound of nuts. And this is kind of a nice trail mix then. This is mostly just nuts. Now, thinking about this, nuts were $6 per pound. The mix that we're putting together of nuts and raisins only drops down to $5 per pound, and raisins were cheap. So it makes sense that you only added a little bit of raisins into this mix to drop the overall cost to $5 per pound. And that's why we're seeing 80 pounds of nuts altogether. It just seems to pass the smell test on this. If it said like 10 pounds, and these were $6 per pound, no way would it be around $5. It'd be closer to the $3 because then it's mostly raisins. Last thing to do is just take the value for n here, substitute it back into this location. So r equals 120 minus 80 for n. Then finally, r is going to be equal to 40 pounds. So we got it, folks. The total poundage was 120, so it is comforting to see the 40 and the 80. They total 140. And it's telling us 40 pounds of raisins, 80 pounds of nuts are going to go into this. Mix it together, and it should be at $5 per pound. Well, any questions at all getting to the end solution on this one? Okay, I have steps 1 through 3. I should probably write in step 4. Step 4 was just to solve the system of equations. I'm thinking about pretty much every equation we solved, it was always this process. If you're doing this one as an exam problem and you had extra time in the exam room, this is another good idea to think about. What's a good check? Well, it's not so much checking on this equation. We can see at a glance that 40 plus 80 is 120. We might wonder, do we really come up with $600 when Kurt buys 80 pounds of nuts, 40 pounds of raisins? So let's check on this equation. It's going to be 6 times n, 80 pounds, plus 3 times r, 40 pounds. And yeah, that comes out to $600. So expensive Costco trip, I guess. Well, the next problems are pretty much just different kinds of situations, sort of like this one here. Even when we go into the simple interest problems, really it's the same kind of idea. Any last questions before we try out another? Okay, here's the next interesting situation. Imagine again for this one that you're in some kind of chemistry lab. Maybe this is in a class, something along those lines. I always found this language to be odd. When we say solution, we don't mean a math solution. We just mean some kind of liquid. We want to know how many gallons of a liquid that is 20% acid, so 20% acid per solution, should be mixed with some other liquid, a 30% acid solution, in order to produce 100 gallons. So this is some big industrial work, it turns out. 100 gallons at the concentration of 23% acid, whatever kind of acid that is, maybe hydrochloric acid or something like that. So we have two kinds of acids, one at 20%, one quite a bit more concentrated at 30%. It looks like we're going to be using primarily this solution here and just bumping it up, increasing it by adding a little bit of the 30% solution. If this was like at 29% we were going for, then we'd be using mostly the 30% acid solution and then just slightly diluting it with the weaker solution. But since 23% is closer to this, we're expecting most of it should be this solution here, this liquid. Like before, we need to start breaking this down. The two unknown quantities are the 20% acid solution and the 30% acid solution. The question was how many gallons? So our answer can't be as a percentage. It's going to be just a number of gallons. So let's break this down similar to the last problem. I'll go with the X and Y here since no interesting variable name really jumps at me from 20% to 30%. So I'll call this X. X is going to be equal to the number of gallons for the 20% acid solution. Then likewise, this is the different liquid we're using. Y is going to be equal to the number of gallons for the 30% acid solution. Takes a minute to just write that down, but you know, your subconscious is thinking about the whole problem the whole time, so it's a good effort to put in. Now, just like in the last problem, there's a couple things that we can put together for certain kinds of totals. There was a pound total in the last problem. That was this equation here, that the total pounds was 120. And there's also a total cost that we had to put together. So, working along similar lines, this one has a total gallons, 100 gallons altogether. So let's write that out as our first equation. Total gallons is just straight out told to us is 100 gallons from the given information. We get to 100 gallons just by adding the gallons contribution from the first liquid and then the second liquid. So X plus Y equals that 100 gallons. Really algebraically, it's the same sort of process, just a different number here, a different context for what X and Y is. So that's kind of nice. So we want 100 gallons at this concentration. So that means of the 100 gallons, 23% of it is pure acid. That means we have a different kind of total this time. Total amount of pure acid in our mixture. Well, if it's supposed to be at 23% concentration, or in other words, 23% of it is acid, all we do is we take that decimal, or excuse me, that percent number there, convert it into a decimal, 0.23, and multiply it by the whole volume, the 100 gallons. So this would give us 23% of the 100 gallons, which is pure acid. So the percent went into this row. And, you know, that might seem similar from the last equation. Let's bring it down just as a comparison. There's some really strong parallels with these kinds of things. The last equation, the total amount was total cost here, not of pure acid, but we still took the 120 pounds, which is like the 100 gallons, and we multiplied it by the cost per pound. Here we're multiplying just by the percentage that we're trying to get to, a 23% acid solution. Then on the left-hand side, we started using the variables. We took the $6 per pound for the nuts. Over here, we do almost the same thing, except we want to know how much of the first liquid, the first solution, is acid. We take the percent, go 0.2, multiply it by X, and that's the same analogous thing as what we were doing right down below here. Then we add to it. To get this amount of pure acid, it came from two solutions. So we add the same thing here. Y is the number of gallons of the 30% acid solution. So take 0.30 times Y, and it tells us how many of these gallons Y was that pure acid. So now we have a pure acid equation, analogously doing something very similar to the very last problem. Well, our equations are set up. All we need to do is maybe multiply this through and start solving them. Any questions first with what we have so far? Okay, well, our equations are not too bad to solve once again. X plus y equals 100 gallons. There's not much to simplify here. This one we could rewrite in a slightly more simplified form as 0.2x plus 0.3y equals 23 times 100 is just 23. I could think again, substitution method works just fine for this. And let's go for, you can solve for either x or y, it's totally up to you. I would solve for x on this one and go x equals 100 minus y. So that whole thing for x is going to substitute here on the right-hand side. We just have to be mindful of parentheses. 0.2 times 100 minus y plus 0.3y equals 23. Now, next thing is to distribute the decimal number 0.2 into the group. 0.2 times 100 is just moving the decimal point 2 spots to the right. So this turns into 20. Then it also multiplies the y, giving us a negative 0.2y plus 0.3y equals 23. Combine like terms, again, it's pretty much the same process as before. We have 20 plus a 0.3y. You can think of this as a minus a 0.2y, just leaves a 0.1y is 23. Subtracting 20 from both sides gives us just 3 now. And when you divide by a 0.1, it's kind of like the opposite of multiplying by 100. This is going to move the decimal one spot to the left, to the right on this one. So this is going to be y equals 30, and unit for this was gallons. This is now 30 gallons of the more concentrated 30% acid solution. And notice that kind of meets our expectation. We were taking something as 20%, just increasing it a little bit up to 23. So it makes sense we shouldn't use too much of that, just 30 gallons. By the way, it's a coincidence if the 30 came out as a 30 here and here as well. Any questions so far to this stage? Okay, again, yeah, that's a kind of an unfortunate coincidence on this one. If you change the 23% to say 24%, these numbers would have been quite a bit different. Change it to 22% different still. So this is not, unfortunately, a pattern in the problem for a quick shortcut. Different situations are still going to need the whole algebra. Well, next thing to do is just substitute back in for y right here. We have x equals 100 minus 30 gallons. So that's our value for y substituted back in. And we're just totally done right at that step. X equals 70 gallons. Forgot to make this one plural on the right for y. So that's our second run at the mixture problems. Really, they're pretty much the same, example 1, example 2. Only difference are the context and the fact that we were using percentages this time. So the big takeaway was moving from the 30% to the 0.3, the 20% to the 0.2 was essentially the only major thing new with this problem. But we'll try out some other new contexts. More stuff with percents should be coming in on the next problems. And this is the first set that's going to involve a couple formulas along with it. Well, not a couple formulas, just a single formula. Well, this is kind of an interesting kind of context here. We're dealing with simple interest. And really the purpose of simple interest is just to give us some quick algebraic problems to work with so that we're not doing bona fide financial kind of stuff. The algebra starts to get worse and worse the more we make the interest, like compound interest, be realistic in the problem. It's unfortunate because simple interest is really something you're probably never ever going to get from a bank. You might get it from a relative who's kind and generous, maybe a parent or a grandparent. So even though it's kind of a silly, not super realistic context, think of doing simple interest as just a first way to think about finance. And it leads into compound interest the more realistic type problems later on with more algebra under our belt. First, let's take a look at what the formulas are saying. If I denotes interest earned, or just interest, P is the amount you put in the account, or principal amount invested. Sometimes we just say simply the principal. If R is then the interest rate, and T is the amount of time, then the amount of money gained in interest, not the total balance of the account, but the amount of money just from interest itself, accumulated after T years, is found through this formula. Interest is the principal amount invested multiplied by the interest rate times the number of years T invested. So here's the next thing that's kind of unusual about this formula. We're going to take T to be just 1 year in the problems that we're going to study. So that means the formula that we actually use looks like this. Interest equals principal times rate, since everything is done in 1 year. And that might give you deja vu, because then it feels like you're doing something like distance equals rate times time. Sure, it's a whole different context. This is principal and rate. There's no time here. But algebraically, you're doing pretty similar kinds of things. So the interest rate R is typically expressed as a percentage, and that's kind of a danger in algebra. We have to convert the percentage we see into a decimal form, but that's exactly what we were practicing on the very last problem, when we were converting things like the 23% into the 0.23. We'll be doing the same kind of things when we're converting the 6% interest into a 0.06. Well, that's the overall formula we're about to use. Any questions about it before we try it out in a couple scenarios? Okay. Again, these problems are strange. Carlos seems like a savvy guy, and he has $30,000 to invest, so he's got some spending change. If he had $30 to invest, he's getting ripped off if he invests this in an account earning simple interest. They are literally ripping him off. He's going to earn way more money if he is in any ordinary banking system with compound interest. But for the sake of an algebra problem, we'll suspend our disbelief and say Carlos is really doing this. Maybe he's loaning to a family member, he's being generous with them and only demanding simple interest. That might be the most reasonable way to think about the problem. So the problem states Carlos has $30,000 to invest. Some of it is invested in an account that's paying 6% simple interest per year. So that's a pretty good rate. And he's investing the rest into an account that's paying 8% simple interest per year. That is a phenomenal rate. When it gets higher than 8%, we worry that it's a Ponzi scheme at that point. After 1 year, he received a total of $2,000 in interest. So hey, that's the I here, the total interest earned. Again, this is only after 1 year, so we're taking year to be 1 every time we use this formula. The question now is, how much should he invest in each account? And that's a weird question all unto its own. I mean, if we need to know that, we could just ask Carlos. Carlos surely knows. So you have to imagine, what context is this going into this? Knowing all this information and not knowing how much Carlos invested in each account, it almost seems like we're doing some kind of money fraud on this case. But again, suspending our disbelief, we can figure this out, so we'll do just that. I think the next problem is slightly more realistic. First thing we need to do is break down what are the unknown quantities. We were told he invested some of the $30,000 into an account paying 6%, and that will be our first quantity. Let's call it X once again. X equals principal invested in the 6% rate account. So that's one variable down. We're told he invested the rest in an 8% account, both earning simple interest. So let's call this one Y. Y is equal to the principal invested in the 8% rate account. So two quantities down, and we have other information. We're told Carlos has 30,000 to invest. And that's a total, that's the total investment. And after 1 year, he received a total of 2,000 in interest. That's, well, another one. Well, I mean, they literally said total here. This is the total interest earned. So here's how we can break this down into two equations, just like before. This is the total investment, or total invested. I think total invested flows a little bit better. The total invested was the $30,000. And this is just going to simply be the amount placed in account X at 6% plus the amount placed in account Y, the 8% rate. Really, all the equations have gone the same exact way on the first equation. The hard part is just knowing that we're using that specific total. How did we know? It's because we said X was the principal amount. It's just $1, not the interest rate earned. And he invested the $30,000. So 30,000 goes there. We can get one more equation. We're completely done. Any questions at all to this stage? Okay, before we jump into the next equation, let's think about what we did on the very last problem because the strategy is still relevant. In fact, when you go to solve this problem, it's going to feel like it's no different really than example 2. It's just a different context, really. So here's what we did on the very last problem. It was the total amount of pure acid, but it's a different context this time. This time, we're talking about a total amount of interest earned. So total amount of earned interest, we're going to get $2,000 is what we're told. So $2,000 altogether. Only difference here is that $2,000 in interest didn't need anything multiplying it, whereas in the last problem, the 100 gallons needed the 23% to multiply it. Here, we just put it in strictly as the 2,000 that was cited there. But now we're using the interest as principal times rate. There's interest earned in the 6% account. The way we get the interest for that is we take X, which is the principal, multiply it by the rate. Well, the rate is looking at us right here. It's 0.06. I'll put it in front of the X since we're just used to seeing the coefficient to the left and then the variable to the right. Plus, this was just interest coming from the first account, X. Interest in the second account was take the principal P, that's the Y variable, multiply it by the interest rate, that's the 8%. To convert that to the decimal, just move the decimal point, which is here, 2 spots to the left. Now it's at 0.08. And that's identical to what we did over here. So the left-hand sides match up. The right-hand side, we just cite the amount of interest, and then we're on our way. This didn't have to get multiplied by anything. Well, that's using interest as principal times rate. Still not as hard as the uniform motion problems. In fact, example 3 algebraically looks almost identical to example 2. With these two equations down, we're now ready to just tackle them any way that seems about right. Any questions at all to this stage? Okay, we've used the substitution method on essentially all the problems so far on these notes. I think the substitution method would work great again on this one, even on example 4. How about we do substitution method one more time because it looks like a good way to solve it. But then on example 4, we'll change it up to the addition method just to refresh on what that looks like. And maybe you feel like that's the easier way to go. So we'll try the addition method on the next example. So for doing the substitution method like before, just pick a variable, any variable, and solve for it. Sometimes a good way to go is to solve for the one that has the higher number, so there's less negatives involved. That's the only reason I would personally solve for y here, but you're going to get the same exact result either way you go. So if we go with solving for y is going to be equal to x. Well, let me try again. We're subtracting x from both sides, 30,000 minus x. You know, I think I said that backwards or thought of that backwards. If we solve for y, we will get a negative in this problem. But let's keep on going just to emphasize that's okay when that comes up, and we'll show the algebra to maneuver through it. Now, once we get to that point, we're going to have a 0.06x plus a 0.08. But right exactly where y is, we put down this expression, 30,000 minus x is set equal to 2,000. Now, not a bad time to reach for a calculator on this one. I need to take 30,000 multiplied by 0.08, and this comes out to 2,400. So on the left here, copy in 0.06x plus 0.08 multiplies here first. That's the, I already forgot, must be late, 2,400. Then 0.08 also multiplies here, so negative 0.08x equals 2,000. So that's our equation so far after distributing. Let's combine our like terms. We have 2,400x, or excuse me, 2,400, and now it's 0.6x minus 0.08x. We get negative 0.02x altogether, equals 2,000. Being careful with negatives, we're now subtracting 2,400 from both sides. It gives us a cancellation on the left, so just a negative 0.02x equals 2,000 minus 2,400 gives us negative 400. Those negative signs are lining up just right. When we divide by the negative 0.02, we'll get a positive on the right-hand side. So negative divided by negative gives us that positive. Didn't mean to disappear the notes. Here's the calculator back. Negative 400 divided by negative 0.02 gives us $20,000. So $20,000 went into the account earning 6% simple interest. Seems kind of weird. You might wonder why put more money in the account earning less, but maybe it's just for the sake of stability. Maybe the higher percent simple interest is a volatile account. Maybe this is in the stock market, maybe not with simple interest, but that would be a danger if it really was in the stock market to not put so much money in the higher interest, more volatile account. But we now know somehow by reverse engineering, same process as example 2, Carlos invested $20,000 in the 6% rate account. Any questions on getting through the equation side of this one? Okay, after getting that number, we're basically done, right? Go to where the variable y is. Y is equal to 30,000 minus our value for x, which is 20,000. That's a fast computation, and it tells us y equals $10,000. So $10,000 was invested in the 8% simple interest account. We've got it. Those are the two amounts invested. And now I guess we could inform Carlos this is what you invested in case he forgot. Maybe that's what's going on. But that's how these kind of problems go. Notice the role of interest equals principal times rate. not as heavy as when we did distance equals rate times time. Really, it was all just a matter of putting down the total interest earned. And once you have the variable listed out, we just took 0.06 times x, dropped it in. That was literally just putting in a principal that was x for p, rate was the 0.06, and same for y. Y was the principal, 0.08 was the rate. Kind of funny looking at it because it's backwards, but we just use the interest twice from this formula above, and set it equal to the total interest. We'll practice this one more time just to get a good feel for how this one goes. But I hope you feel like this one is very, very similar to what example 2 was. Write down a total equation, convert percents into decimals, and have a total interest equation. Well, let's try this out on the very last one. So this one is slightly more realistic in a way. Sorry, talking's a little hard today for some reason. It's still talking about simple interest. Let me see here. Never we said simple interest. We should just imply that somewhere in the problem. Let me put in a little revision. He'll invest some of that money in a short-term CD that pays 12% interest. The rest of the money market savings account pays 5% interest. Let's say here, assume all interest earned is by simple interest. That's our assumption in the problem, but I feel like we really have to bake that in to be specific. Or else the problem just seems kind of funny in a way. So this time it's Mark. Mark is investing $10,000 to pay for his daughter's wedding next year, so very generous guy. He will invest some of the money in a short-term cash deposit that pays 12% interest. That's a humongous amount of money. And the rest in a money market savings account that's paying $5,000. That's a lot for money market savings as well. These problems are kind of interesting where the interest rates just seem super optimistic. But let's write down this as our first quantity. I'll just briefly name this x equals amount invested in the 12% account. The rest is in a 5% interest account. So that's our second quantity. We'll call it y like before. Y equals amount invested in the 5% account. So it's a different context, different scenario, but really same kind of story as every single example on these set of notes. We write down two equations. One of them is a kind of total, and that's just going to be the total invested. So total invested is going to be equal to $10,000 and we already said x is the amount invested and so is y, so we just total those together. So go x plus y. It's now set equal to the $10,000. Well, we're on our way with that. Now we have this amount. Mark wants to earn $1,095 in interest in 1 year. So he's investing $10,000 to pay for his daughter's wedding. What we're wondering now is maybe this is all he's actually paying. He's just going to pay $1,095 to the wedding, and he's going to pocket this again after the year is up. Or maybe he's giving $11,095, taking the principal plus the interest earned and giving it all to the daughter. Who knows? There's a little bit of drama in this problem. I'm starting to suspect by the wording in this problem, this is all he's giving to the daughter, the $1,095, and then he's just going to reclaim his money after the year goes by. But when it says he wants to earn $1,095 in interest, that's the total interest equation. So total interest this is going to be equals 1,095. And we set it up exactly like we set up the last two problems, in fact. Once we know what the number is on the right-hand side, we go to what we listed the variables are as, and if this was the 12% account, we just convert this to a decimal number. Move the decimal here, 2 spots to the left, so it's a 0.12. This is an interest rate, multiplied by the amount invested, which was just X, and that's how much interest came from the first account at the 12% rate. Because it's total interest, we do the same thing with the second account. Take the rate. This is a 0.05, so that moves 2 spots to the left. Multiplied by the principal invested, amount invested, which was Y, and that's 2 equations down. Well, if we can solve these equations, we're on our way. Any last questions at all, folks, on writing them down? Okay, I'd say this one does pretty good just solving by substitution, again, even on this one. But we promised some variety on example 4. So let's show how we solve these if we want to do it by the addition method. Here's what I would do. For the addition method, I would stack them on top of each other. X plus Y equals $1,000. Then 0.12x plus 0.05y equals 1,095. And we need to eliminate one variable, maybe it's x, or the other variable, maybe it's y. You know, there's a good strategy here. One strategy is the decimals make this a little bit more tough than it needs to be. We could just multiply the entirety of equation 2 by 100. That's going to clear off the decimal numbers and give us 12x plus 5y. And the downside is we had a couple zeros over here. Let's go just that route. Multiply by 100. So we get a new equation, 12x plus 5y equals 2 extra zeros at the 1095. So 0, 0, 109,500. So if I copy x plus y equals 1,000 over here, nothing's going to eliminate. But notice you can do other stuff to this one. In view of having a 5y here, let's multiply that top equation by -5. So we can get a -5 in front of the variable y. We could have gone for eliminating x, but that's involving multiplying by -12. The numbers are even bigger. So I think multiplying by -5 is probably the easier route on this one. So this equation transfers over here where we multiply by -5, both sides. So we'll get to -5x minus 5y equals, now this is -50,000. We're ready to go with the addition method now because variables will eliminate. The y variable is eliminated. So tally these up and we get 7x on the left equals, you know, it's late on a Thursday, so let's treat ourselves to a computation on the calculator. Should be able to do this in my head, but I want to be really sure I get this right. It's money after all. You have to be careful when you're dealing with other people's money. So this comes out as $59,500. Well, I shouldn't say dollars just yet until we solve for x. 59,500. Last thing to do is just to divide both sides by 7. Division by 7 is going to give us 8,500. So $8,500 is invested in the account earning the 12% rate. which is most of the money. So this person is trying to maximize. We wonder why even use account Y, but maybe there's a good reason for that. This person's trying to maximize interest. Getting $1,095 is partially done by dumping most of the money in the higher rate account. That's one variable. We still need the amount in the second account, but there's a whole bunch of equations everywhere now. We'll just pick the simplest equation. I vote this one, x plus y equals 1,000, and just solve for y there. It's a good idea to just copy it down again so it's not getting too crammed up in there. X plus y equals 1,000. Excuse me, 10,000 rather. We're plugging in the value for x. So we'll have 8,500 plus y equals 10,000. Subtract 8,500 from both sides, and then y is going to be equal to $1,500. So that's the amount that Mark should invest in the second account. 8,500 is the amount Mark should invest in the first account if he wants to earn the 1,095 interest in 1 year. Problem is slightly more realistic because no money hasn't been invested yet. So it's like you're the financial advisor here. You're probably wondering why simple interest, but again, that's the algebra part of it. We're trying to stay away from compound interest until we have a lot more algebraic machinery to help us with it. But we did it, folks. That's the rundown of pretty much all the problem types you're going to see in this section. In particularly 4.3, just about every problem looks like this one in the setup. And we solved it a separate way just to give the addition method some attention since we did the substitution method on everything else. Well, any last questions or comments at all before we close out these notes? Okay, well, we did it, folks. We're done with chapter 4. I think chapter 4 is intense because section 4.1 seemed like ordinary friendly algebra, just two equations, but really chapter 4 was all about doing lots of applications. So congratulations, we got through that. Chapter 5 is returning to more of what an algebra class is going to really look like. We're going to do selected sections here, starting in section 5.2, dealing with properties of exponents. Exponents are things that people sometimes in this class can be really well fluent in, or sometimes you might be pretty rusty in it. So section 5.2 is a kind of getting everyone all on the same page type of section. To give us some extra support and materials, you might want to take a look into the document Exponent Laws. We have to memorize these laws for the sake of exams. The math department has required our exams be closed notes. So this is a good set of notes to become familiar with. It seems like a lot, but the more we practice these kind of exponent laws, these really do become second nature. The goal is just to see what all the formulas are that we take for granted, and then start using them as if they're second nature. So on the left column is the name of the law, the actual formula for the exponent law, and a numeric example, since sometimes it's nice to see this as a concrete numerical example. The second, I guess you could call it a handout, this PDF right here, is if you just want to do some really fast drill problems. Maybe you're studying before exam 2, maybe just freshening yourself up before doing the homework. This worksheet looks like this. Exponent rules and practice, it's just a listing of a whole bunch of problems. And even more problems, this is the practice side. What you'd want to do is take out a separate piece of paper, cover up this part here, these are all the answers, and just run through them. Solve a bunch of them just as a warm-up maybe select some at random, maybe go for the challenge ones. And you can check the solutions down below really quickly as well to see how well you're doing on these kinds of problems. So that's what section 5.2 is going to be all about. We take a look into the notes. Here's how I have it organized for us. We're going to go and look into the laws just one at a time. First, we'll define what we mean by an exponent, crank out some numerical results. Then we'll start looking into each one of the laws, first with the product property, then with the quotient property, zero exponent property, and so on. These notes are kind of long, but the problems go pretty fast. So these notes are just meant to be kind of a roadmap through all the properties of exponents that we're going to need to know for this course and other math courses beyond. I think we could start some of these problems, but this might be a better problem to come, or a better set of notes to come back to once we are back in class on Tuesday. We'll start off right here, run through the notes, and possibly start the next section as well. So we'll end class today about 5 minutes early. Any last questions or comments before we call tonight? Okay, well, have a great night, everyone. I'll see you all next week.